So, ladies and gentlemen, it's a pleasure to welcome you to our second public lecture of Frank Leymann. Frank Leymann is our Kurt Gödel Visiting Professor of TU Vienna, TU Wien. He's well-known, world-renowned, known for his work in workflow management and middleware pattern languages. He's IBM Distinguished Engineer, and I guess one of the few he decided after becoming this rank at IBM to go back to academia. And since 2004, he's professor for software system architecture at the University of Stuttgart. More importantly, at least for his presentation today, he has a PhD in mathematics and a bachelor and master in physics and mathematics. And I guess this is was the motivation for him to go from workflow systems to quantum computing. And he, since several years now, is kind of one of the front persons in the area of quantum software development in Germany, in Europe, and beyond. I am really very happy and honored to have Frank here, albeit only virtually, but you know, we are already used to adapt to lockdowns. So please join me in virtually welcoming Frank for this presentation, and we are really looking forward to your presentation. If you have questions, please write them in the chat, or after the presentation we will have time to also make a question answering session. Frank, it's your floor.
Thank you very much, Gertie. Thank you. So this, because I gave an introductory talk a couple of months ago, so this is not an introductory talk, just as a warning. So I do assume that you understand what qubits are and what quantum registers are and what gates basically are. And on top of that, I start now because I'm running a couple of projects that build real-world applications, and there is a lot of learning involved. And at the sudden, there comes a bitter truth about quantum algorithm in the NISQ era. So what I'm going to discuss today, first of all, are what are the technical problems we have today in order to build applications. Well, the first thing is decoherence. That means the qubits, the information units, are not really stable. They decay over time, often rather quickly. If you have several qubits, they may disturb each other. That means it is difficult from a technical perspective, from a technology perspective, to scale quantum computers. That means increasing the number of qubits is quite different, although IBM, for example, announced that they have early next year 127 qubits and more than 400 in 23. The other problem is gate infidelity. That means, as I will show, each operation on a quantum computer is a little bit imprecise. That means if you run a lengthy algorithm, then the errors, they basically add up. Then you have readout errors. So if the quantum computer completed and came up with its result, then the results are a little bit imprecise, right? And I will discuss that. And finally, one problem is qubit connectivity. Qubit connectivity basically means that you have, as I will show, you need 2 qubit operations in order to come up with a universal quantum computer. And these 2 qubits that you want to manipulate jointly need to be connected, technologically connected. And this introduces errors. And if they're not connected, you need to have additional operations to swap the qubits until they are technically connected. That means the number of operations does increase and the whole system becomes more and more unstable. So this is the problem scope we're in that I'm going to discuss in this presentation. So what is decoherence? Decoherence basically requires me to remind you about the Bloch sphere. A qubit can always be represented. So this is the famous ket notation. A qubit can be represented as a superposition out of 0 and 1. And the amplitudes, the coefficients of the 0 and 1 vector are these things here. So you have an angular theta and an angle rho. And this angle theta and rho can be taken as a two-dimensional thing that you can basically uniquely map the qubit to a point on the unit sphere by having theta from the z-axis and rho from the x-axis to the projection of the qubit. And so two coordinates suffice in order to present a qubit on this sphere, the Bloch sphere. So a qubit is a point on this surface of a three-dimensional ball. That means a two-dimensional sphere. And if you have a qubit here, the qubit may, based on environmental interaction, relax. And relaxation, the T1 time, basically means you transit to the orthogonal state, or the qubit may a little bit shed around. That basically means it dephased. That means one of the phases basically has a small disturbance. This is the T2 time. T1 time and T2 time are very fundamental characteristics of a quantum computer. Being a computer scientist, what you could basically say is, well, this is not a problem. Bits may also decay. What about using error correction? Well, error correction is not really applicable in the sense that we understand it in computer science, in informatics, because you cannot take redundant copies of one and the same qubit, because there is something that's called the no cloning theorem. You can prove that you cannot copy a qubit. It means all that we learned about redundant codes and so on cannot be applied. A different kind of technology needs to be invented. And a qubit is, a bit is 1 or 0, but a qubit is any of these uncountably finite points on a Bloch sphere. And if it only changes a little bit, what you have is you have continuous errors and not discrete errors, completely different from classical error correction. And you cannot basically read a qubit, because reading is destructive. If you read, you do a measurement, and the measurement then decides the qubit to become 0 or 1. That means if you read it in order to correct it, this can't be done, because you lose basically the state. So destructive reads are destructive. What people do is they invent error correction codes. Here I present a code called the Shor code. What that basically means, a single qubit is then represented by 9 other qubits. So out of a 0, out of a 1, you require 9 qubits and create this beast here. That basically means in order to make a qubit stable, you need much more physical qubits to result in what is called the logical qubit. So a logical qubit is a qubit that is error corrected. And you need a bunch of physical qubits in order to become stable. And by the way, using this 9 qubits is only a first step, because then you are only protected from a single error, but multiple errors may happen, or the other qubits that provide redundancy may also decay. So you need up to 1,000 qubits, not physical qubits, to result in a logical qubit. That basically means multiple of these noisy physical qubits need to realize one stable logical qubit. And if you accept noise, what you do is you need to, so this thing here, I need to encode the 0 or the 1 in this equation here. That basically means I need to encode a qubit into many qubits in order to result in a stable or into an error correctable qubit. So this is what you need to do first. Then you perform your algorithm, and during the algorithm, some noise happens. And then you must have an error correction circuit. That basically means you need to detect which kind of error happened, which is called syndrome recognition. And once you detected the kind of error, you need to have a recovery circuit here. That means encoding, algorithm, or performing certain operations. That means performing a certain gates, and then doing error correction is a pair that embraces a single step in an algorithm. That basically means the algorithm are basically blown up, as I will show. Then gate fidelity, or better, gate infidelity. What I presented in the first talk about quantum computing was that we call a set of 1 qubit operators, which are basically unitary matrices, universal if 1 qubit operator is a finite combination of this universal set of operators. And if you have one of these qubit operators, then you can easily prove that what you do in lectures, and some of you may have attended the lecture I gave here in the summer term, each gate, one qubit operator can be represented as rotations on the Bloch sphere around the z-axis, the y-axis, and the z-axis, again, around the angles beta, gamma, and delta. So that basically means each rotation, each one qubit operator is a composition out of rotations on the Bloch sphere, but typically the Bloch sphere operations are imprecise because I need to rotate around non-rational angles, and rotating about irrational angles, except multiple of pi, cannot be done very precisely. That means each of the rotation has a very small error. That means then that the whole gate has inherently a small error. And these errors keep piling up because an algorithm, a quantum algorithm, is a composition of a bunch of unitary operations. That means if you start with your input value, the algorithm produces an output value phi t, where t is the number of the gates that I do apply. And each of these unitary operations is a little bit imprecise. That means instead of ui, the quantum computer will perform this ui tilde. That means if I start with phi 0 and apply the first gate, I result in phi 1. This is what I want to have, but in fact you get u1 tilde of phi 0, which is phi 1 plus a little of an error. And this error is called the gate error, or the lack of gate fidelity. And if you continue, if you now apply U2 and so on by induction, you basically prove that the computation of the algorithm is this disturbed result. And this is here this telescope formula. And on the next slide, I refine this. That means the error, if I compare the computed result with the ideal result, well, is really piling up because each gate that I apply has a certain error. That means if I can control the error of each gate, right? If I know that each gate UT compared with the really performed gate UT tilde is less than a certain threshold epsilon, right? Then each algorithm that contains T steps, more precisely T layers, as I will explain later on, right? If you then the accumulated errors, they are growing linearly with the length of the computation, which is quite good if it only grows linearly. So this is called error propagation. And then many years ago, somebody proved the threshold theorem. The threshold theorem basically says for any required precision of a computation C of ideal gates of a quantum computer, there's an implementation C prime based on fault-tolerant gates, and I will explain what a fault-tolerant gate is on the next slide, that computes the result C with the required precision that I prescribed before. And here's now the condition: if the fault-tolerant gates fail less than a certain threshold eta times. And today, that means 2 years ago, eta was only 1% of the gates may fail. That basically means fault tolerance scales in principle if a vendor of a quantum computer can guarantee that the maximum error of all the gates have a joint threshold. So basically fault tolerance scales. And this is achieved in today's machines, which is called noisy intermediate scale quantum machines. NISQ, in analogy to RISC and KISQ that we computer scientists all do know very well. And what do I mean by fault-tolerant gates? First of all, the principles of fault tolerance said in order to achieve a single logical qubit, a fault-tolerant qubit, I need to use K physical qubits, noisy qubits, in order to get some stability to protect the qubit from decoherence. If I do that, right, if you take now a look at a certain gate, the gate works on a logical qubit. But in fact, because the logical qubit consists out of a bunch of physical real qubits, I need to implement the ideal gate G by a subroutine G prime. What I did here is a little example. This is a C not gate, a controlled not. It's an if-then statement. right? And I need to implement the if part and the then part as subroutines on the bunch of on the block of physical qubits. And once I do that, even if I have an error-corrected gate performed, I need to perform error correction on each on the involved qubit to find out whether the state of the qubit has changed on the block of physical qubit, and I need to do that. That means after each error-corrected gate, I need to apply error correction in order to correct the error and then apply the next gate. So the whole circuit is basically blown up. So the implication of noise is I need n noisy physical qubits to realize one stable logical qubit, and n is seriously up to 1,000. And more qubits are needed that estimated the theoretical algorithm. So theoreticians basically are very proud and they prove I have an exponential speed up. But if you really take a look at it and apply error correction, there is the real jeopardy that the exponential speed up is basically destructed. And we are going to discuss that further on. And a single universal noisy gate must be realized by quantum subroutines, and I must run error correction on noisy qubits periodically. That means I need much more operations than estimated by a theoretician that invents a very, very fine and new quantum circuit, quantum algorithms. So how do you measure now the feasibility of successfully running an algorithm on a quantum computer? So we need to define the depth and the width of an algorithm. The width of the algorithm is the number of qubits that an algorithm manipulates. And the depth of an algorithm is the number of layers. And each layer is defined as a bunch of gates that can be performed in parallel by a quantum computer. So the depth is the number of these layers, and the width is the number of qubits that is manipulated. As an example, here I do have a circuit, and the circuit has obviously, the designer says these are the three circuits, but you can see is that this gate can be moved over there because there is no data dependency between these two gates, and there is no data dependency these gates and these gates. So I can basically eliminate this layer, and what I get out is this circuits by a simple rewriting. That means the algorithm really has a depth of 2 and the width of 7 because all the qubits are manipulated. But this algorithm here, I can move the S gate over here, the H gate over here, the T gate can be moved over here. So what I get is I get a circuit that has the depth 3 instead of 1, 2, 3, 4, 5, 6 that the designer basically has laid out. And it has a width of 3 because this qubit is not manipulated and this qubit is not manipulated. So I only need 1, 2, 3 qubits. So these algorithms are noisy because the gates show errors and the qubits show errors. That basically means the number that is of real relevance is the product of width, the number of qubits manipulated, and the depth, the number of sequential layers and parallelism goes on in the sequence. And the product of W times D must be significantly less than 1 divided by the error rate of the quantum computer. Right? And this has implications. You may decide that you want to have deep quantum algorithms. Your algorithm needs many, many different gates that run sequentially. That basically means in order to perform it on today's quantum computer, you must have a small width. You are only allowed to manipulate a very few qubits. But if you only manipulate very few qubits, you can efficiently simulate that, right? Because you can transform a circuit into linear algebra, and then you perform linear algebra on a admittedly huge machine. So deep algorithms that need many gates and only use few qubits can be simulated. So what we are looking for in order to prove the advantage of quantum computing is shallow quantum algorithms. Algorithms that manipulate many qubits and have only very few sequential steps involved. Right? In the first talk that I gave a couple of months ago, I basically said, well, take a look at 50 qubits. 50 qubits correspond to 10 to the power of 15 different states that can be manipulated at once in a quantum computer. And you need then, if you have 50 qubits, you need a 10 to the power of 15 storage in order to manipulate, to simulate the circuit. And 50 is today the limit that you cannot simulate anymore, right? And as I mentioned before, there are vendors that have already more than 100 qubits available. This is 10 to the power of, beat the hell out of me, very huge. You can't simulate it. And here's the potential for quantum advantage. So what happens in a quantum computer? What happens there is called transpilation or cross-compilation. So what happens is, this is the circuit that you basically program. This is the graphical representation, and I presented last time that there is an assembler language called OpenQASM, quantum assembler. Here's the textual representation. And what the machine does is it transpiles it into a circuit that looks a little bit different. These two gates are basically transformed into 3 rotations on the Bloch sphere, U3. That means there is no negation X and there is no Hadamard gate. Hadamard gate, if you remember what we discussed before, Hadamard gate is used to introduce superposition in a quantum computer, and superposition is one of the 3 or 4 resources that provide quantum advantage. So the quantum computer, in order to execute a given circuit that you design, that you program, needs to transpile it, needs to rewrite it, because the computer does not support this gate and this gate natively. Here's a typical example. The typical example is that the depth of the circuit is increased, significantly increased. So the designer here, the programmer, had a circuit of depth 3, 1, 2, 3. And what the transpiler does out of it is this here. This is of depth 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a 3-time increase of depth. And this is what typically happens. If you have a very nice circuit, you are very proud of your circuit, you transpile it for execution, then you detect at the sudden that the circuit is significantly expanded, way too long to be performed on today's machine. In very rare situation, the depth may be decreased, but this is only an exception. Most often, the depth is increased. And the same circuit can be transpiled very differently based on the target machine. What I've done here is I transpiled the circuit to be run on a QPU, and here, for example, on a simulator. Right? If I would have taken a different QPU, the circuit may look different than from this QPU, but I took here a simulator just to show you that different transpilation of the same circuit may basically happen, significantly different transpilations. That basically means the depth of the circuit can often be reduced by shifting gates from right to the left, as I have shown a couple of slides ago, without sacrificing the data flow. So if one gate produces state that another gate needs, you can't move it. So you must not break data dependencies in order to do this little optimization by shifting gates from right to left. And the rewrite that the quantum computer does is hardware dependent. That means, first of all, the gates that I use in my algorithm must be mapped to the gates that are implemented on the machine, on the physical machine that I use to execute my gate. And this increases typically the depth of the algorithm. That means it's a good idea to take a look at this transpiled circuit and in order to assess its executability. And I will come back to that in the last 10 minutes when I discuss a component that we built at my institute. The next is now input preparation. So what happens is typically you do the following. So this is, by the way, the rough structure of a quantum algorithm. This is here the real algorithm that the quantum computing folks or the quantum physicists do invent. And I will show you now that you need a certain step that is called the state preparation in order to prepare the input data that the algorithm needs, and then you need to perform measurement. So this is basically what the papers focus on that you read. And this step is something that you need to prepend and append, which involves classical preprocessors. The dashed boxes basically means here happens something on a CPU. And here's now a typical situation. You take a look at a certain quantum algorithm that you read in a paper. Here is a very, very famous paper that explains how to solve linear equation systems based on quantum algorithm, the so-called HHL algorithm. And then you browse through the paper, you find a bunch of mathematics. This is the whole secret behind the algorithm. And then you take the end to do the following. You transform the math into a quantum circuit. This is often still done by quantum computer specialists, right? Because this math, you must understand how this math basically maps to some unitary stuff here. Then you have the circuit. You are very proud. You want to transform this circuit. But then what happens is you take a look at the paper, and what the paper says is we need an efficient procedure to prepare. So the paper proves that it gets an exponential speed up in solving linear equation systems compared to the best known classical algorithm. But there is this tiny sentence. There's another paper called Read the Fine Print. There's another sentence, so you must read the fine print that says we need an efficient procedure to prepare B. Well, that means the input vector must be prepared as a quantum state, which basically, so you must prepare data points, individual vectors or set of vectors, and the matrix must be prepared. Sometimes you need textual data that are transformed into numerical data, which is what Johanna will explain at the end of the week. You need to prepare other formats, qubits, and so on. So this innocent assumption basically means that I need to prepare the state. And what that basically involves is I need classical preprocessing. I need classical preprocessing, and I give you an example. I discussed that later on. This is something that I need to do on a CPU. I need to generate circuits out of the data that I want to pump into the quantum computer. I generate these circuits, and this circuit must then be run on a quantum computer in order to prepare the input. To prepare the input that is then processed by the HHL algorithm, right? So the HHL algorithm, this was what is prepared in the paper, and the paper asks you to prepare this B efficiently. Well, and efficiently, is this sufficient? I will discuss that, right? You need to invent something to pump classical data as a quantum state into the quantum computer so that the algorithm may run. And state preparation comes in very different flavors, and you need to find out the pros and cons of each of the state preparation methods. And this, of course, calls for patterns, and we already are in the process of building a pattern language for quantum computing to help people to find the right solutions for recurring problems. So the possibilities that I'm going to discuss is basis encoding, amplitude encoding, tensor product encoding, Schmidt encoding, only to give you some impression. And these encodings fall into two categories. Digital encoding is needed when you need to perform arithmetics, and analog encoding must be performed, for example, if you need to pump data into a high-dimensional feature space to do machine learning, for example. So what is basis encoding? Basis encoding says I have a natural number x. I encode this natural number binary. That means I present x as the sum of xk times 2 to the power of k. And then these components, these coefficients xk, the 0 and 1s, are basically encoding a quantum register state, which is then called a basis encoding. And this is a digital encoding. The digital encoding basically means, well, if I presented my number x as binary coefficients b1 to bn, what I need to do is I need n qubits that are initialized in state 0, and then I perform the Pauli X matrix, the negation. Dependent, if this is a 0, then here I don't modify the initial state. If bn, for example, is a 1, then I perform Pauli X, which turns the 0 into a 1. This is a very nice state preparation circuit, right? It requires n qubits. If my natural number that I want to represent as a state requires n binary coefficients, I require n gates. and the circuit has the depth 1, and I don't need any support qubits, which are called ancillary. Right, and this is here the mathematical representation of the circuit that I need to generate. This can also be used in order to represent real numbers. So what I do is I take a real number and I approximate it in binary representation up to k decimal places. So the part before the comma is the typical binary representation, and the part after the comma is something that you don't learn in lectures. It is quite simple. What you do is you take the part behind the comma, you multiply it by 2, and then the part, you take a look at the result, and then the digit before the comma now is one of the zeros and one the binary representation of the part after the comma. And this becomes periodic, then I can basically stop here, and I know that 1.7 in decimal representation is this string in binary representation. So it's easy to transform rational numbers into a binary representation if you fix the number of decimal places that you need. Right, and here is, so to speak, the circuit that you need. Right, you take the rational number, the real number, compute it in a binary representation, and out of the binary representation, you know exactly what the circuit is that you need to generate. And this circuit is then run as a state preparation circuit to turn the ground state of the quantum computer into a representation that can now be manipulated by your quantum algorithm. And the same applies then to vectors, right? Here I have a vector out of R3, right? These are all real numbers, and I perform the same algorithm that I've shown before. Each of the components of the vectors must be transformed into a binary representation. You need to take care about the sign of real number. What you typically do is you have a leading 1 to represent a minus sign and the leading 0 to represent a plus sign. And this is then here at the bottom of the page, the representation, the binary representation of this vector that you now can manipulate. And in order to pump sets of data, if you want to manipulate sets of data, for example, to compute certain cluster of your data points, right, then you transform each of the vectors of your data set into a binary representation xi, and then what you do is you perform a uniform superposition of these data points by running a proper Hadamard gates here, right? So this is how you pump sets of values into your quantum computer. This is digital encoding. Digital encoding, as you saw, is you need very, very many qubits, because the larger your real values basically get, the longer gets the number of digits that you basically need, binary digits that you need many, many qubits, right? And this is not a good representation on today's machines, where you have 10 up to 100 qubits as of today. The other thing is you do amplitude encoding. What that basically means is you take a vector, and without loss of generality, I assume it's a unit length vector. Otherwise, you divide everything by the norm of the vector. Then each of the coefficient in the linear combination of the basis vector is then taken. So this is then taken. This is the amplitude encoding that you basically do. And this is an analog encoding, right? Because you don't have binary digits. And if this vector is not of a dimension of a power of 2, you do what we call padding. You basically extend the vector space where this vector is from by a bunch of dimensions m, so that n plus m results in a power of 2. What you need is, in order to compute the amplitude encoding, is you need only very few qubits, namely log2 of n, but you require an exponential number of gates in order to prepare the state, which is bad, because many gates basically means you have a typically lengthy algorithm. And by the way, if you don't have a unit length vector, as I said before, you divide it before you compute the amplitude encoding by the length of the vector before. And by the way, a matrix that you need to store in your quantum computer can be represented as a vector, right? You basically linearize your matrix into a vector and then use an analog encoding in order to store it in your quantum machine. There's one problem. The domains in which quantum computers shine today is optimization, is machine learning, and is material science, quantum chemistry. Machine learning typically needs information about the neighborhoods of your data. But what I said before is, if I have two vectors, and bear with me, I only represented in dimension 1. If I have two vectors, and I need to normalize it because you can only pump vectors of length 1 into a quantum computer, because quantum state always is a vector of length 1. What happens then is, well, these 2 points that have a certain distance from each other are basically equated in terms of length. They are mapped to the same thing. This basically means that I have no chance at all to run quantum typical machine learning algorithms on the quantum state. So what you do is you introduce yet another dimension, and you map the vectors onto a unit sphere in this higher dimension. And then to a certain degree, not really faithful, but to a certain degree, the distance information about the points that you want to manipulate via your quantum algorithm is maintained. So this is another trick that you typically do. You normalize while generating some neighborhood, by maintaining some neighborhood information here. Then another encoding is on the product encoding. The product encoding basically takes the components of the vector, again, it's assumed to be a unit length vector, and we interpret the xi's, the component of the vector, as angles of the total vector that I use. So each component is mapped to cosine xi times vector 0 plus sine xi times vector 1, which is this vector. I do it for all components, and then I build the tensor product, because a quantum register is built by using the tensor product of the individual one-dimensional qubits. Right? This is called the tensor product encoding because it's a product, sometimes called the angle encoding because I interpret the components of the vector as angles of this vector of this qubit. And this is again an analog encoding. You require n qubits and n gates. And this is quite acceptable. And this is often used these days. And the circuit is, you need to go back to linear algebra. This matrix is a rotation matrix, right? If you apply this rotation matrix to the initial state vector 0, 0 is the vector, cat 0 is the vector 1, 0 in a two-dimensional plane. That means this rotation creates this vector. So I apply the tensor product of this unitary matrices, of this rotation matrices on the ground state of the quantum computer. And then I get exactly the encoding, this encoding that I wanted to have. Again, this is what also is used today quite often. So what you basically do is you inspect the vector that you want to store in your quantum computer, right? Then you generate this circuit, and this circuit is then represented here graphically. This is the state preparation circuit that basically performs your quantum, that can then be processed by the quantum algorithm. There's yet another important state preparation thing that is called the Schmidt decomposition. I mentioned it because very likely in 2 weeks we will have another talk where I will discuss the miracles of entanglement and how to use entanglement. And we will see in 2 weeks that based on entanglement, machine learning will become extremely effective. You can prove that in high dimension, often a single training data, a single training vector will suffice to train a neural net. And for this purpose, you need to control the entanglement of the data that you pump into a quantum computer. And this is what you can do based on the Schmidt decomposition. So the assumption is you have a vector, and the vector space is somehow represented as a tensor product vector space. And then the theorem of Schmidt basically said is you find an orthonormal basis, uj in V and Vj in W, and then this vector x can be represented as this lambda I times ui tensor vi, and you only need k basis vectors here. And these are the so-called Schmidt coefficients. These are values greater than 1, and the sum of these Schmidt coefficients sums up to 1. And this k is called the Schmidt number of the input vector x, or sometimes also called the rank k. And what you try to do is, this k is a measurement of the entanglement. So the higher k, the more is this vector entangled, right? And you try to control by finding proper Schmidt decompositions, you try to control that in order to have more efficient algorithms, for example, in machine learning. I rush over it because the details are not really important. So in order to compute the Schmidt decomposition, you need to do something that is called the singular value decomposition. In German, Singulärwertzerlegung, singular value decomposition. So you use that. If you compute the singular value decomposition, then you have all the ingredients. You get out, you get 3 matrices out of the singular value decomposition. This is what you do upfront in a classical machine in order to generate then this quantum circuit. So you apply singular value decomposition in order to generate these matrices, to compute these matrices, and these matrices are then unitary transformations that you need in order to build this circuit that then prepares input data that is highly entangled. But the problem is that the quantum computer does not understand unitary transformations on multiple qubits. The quantum computer only understands typically 1 qubit unitary transformation and the C0. So what must be done is that this unitary transform A, U1 and V must be rewritten in tensor products of 1 and 2 qubit operators, right? And this 1 qubit operators must then be rewritten in the rotations that I mentioned a couple of slides before. So a lot of classical work must be done before you have a circuit generated that you can use to pump your data into a quantum computer. It basically means these matrices are refined by circuits in itself, right? And this must be refined. So a lot of stuff is going on. And this is what you do classically. You compute based on singular value decomposition these matrices. You represent them as 1 and 2 qubit operations, and the 1, 2 qubit operations must be rewritten as rotations, and everything must be done classically. Then you have the circuit that can be run. So a lot of stuff is going on. Pre-processing typically means you have a classical step that decides which encoding you need. Do you need a binary encoding? Do you need an analog encoding? Do you need an encoding that ensures some degree of entanglement? Then you need to compute the parameters that you need for it. Then you generate the gates, and out of the gates, you generate your circuit in this assembler, in this custom assembler, which represents then the circuit that must be prepended to the unitary transformation. And then you can run your circuit, the combined circuit, and then you get a result that is in a quantum computer. And this must be measured. This is another subject that I'll discuss later on. So the implication of state preparation is it requires typically many additional operations as well as additional qubits and the classical pre-processing compared to the ideal algorithm that you read in the paper and are fascinated with, right? So this is theory, and then how you make it run practically. The next thing is oracle expansion. So we take a look at this unitary transformation. What you see here is one of the very, very first and most famous algorithm, the algorithm of Deutsch, that basically proved many decades ago that a quantum speed up is possible. It basically solves the problem. I toss n coins. How many coins do I need to toss in order to find out whether which coins are bogus? And this algorithm basically proves you only need to toss once. And it basically says you must bring your quantum computer into superposition. These are the 2 Hadamard gates here. And then a subroutine is applied, which is called an oracle in quantum algorithms. Then you apply Hadamard here again, and then you measure. And then dependent on the result of the measurement, you know whether your coin is bogus or is a real coin. And this UF must be presented as a circuit, right? If you have a function, so you basically toss it, right? 0 is mapped to 1, 1 is mapped to 0, right? Then you can use a controlled C not controlled by 0, right? I'm not proving it here, right? This is, so to speak, the proof. The problem is that this gate is not supported by quantum computers. That means you must expand it into, this is a C naught that is implemented on a quantum computer. And these are here the X's, which are the Pauli X matrices. So that basically means the algorithm, if I go back, says, I'm a very good algorithm. I'm having an exponential speed up if I have this oracle, but this oracle must be implemented. And instead of having here a single oracle, a single gate, I have multiple low-level gates in order to expand it. So substituting an oracle, so often the complexity is measured in the number of gates, and the oracle is counted only as a single gate. And if some algorithms prove a certain speed up, the speed up often comes, not often, comes sometimes because they count the oracle only once. But in order to have real implementations, you must expand it. And that basically means read the fine print, take a look at the oracle, what the circuit behind the oracle must be, and whether the expansion of the oracle into a real circuit diminishes the speed up that the theoretical algorithm basically gains. So this is here the resulting circuit. I expanded it, and instead of having a depth of 1, 2, 3 at the sun, have a depth of 1, 2, 3, 4, 5. And this is now the real famous algorithm of Shor. The Shor algorithm basically allows you to factorize integers. And it looks very slim. It basically says you bring your computer into superposition, then you run an oracle, then you do a quantum Fourier transform, and then you do some classical post-processing, right? The whole secret is Shor basically, so the real secret is this quantum Fourier transformation, and then a continued fraction analysis, right? So Shor is a mixed and hybrid algorithm that consists out of a quantum part and a classical part. But this oracle here needs to compute values of a number theoretical function, a to the power of x modulo n, which requires multiplication, addition, and so on. Let's take a look at what it means to implement this arithmetic on a quantum computer. What that means is adding two numbers is this circuit. I'm not going to discuss the details. It only should give you an impression that adding two numbers is complicated in terms of implementing it on a quantum machine. And by the way, this addition needs quantum Fourier transformation as well as the inverse of quantum Fourier transformation. And this is the circuit of quantum Fourier transformation alone. So this circuit must be substituted for this box here. And if you do multiplication of 3 qubit data, it's a huge circuit that also requires a bunch of ancille, additional qubits. That basically means if you take a look at Shor's algorithm that looks very slim and fascinating, well, you require the computation of a number theoretical function on a quantum computer, which requires a bunch of rewrite, a bunch of additional steps and additional qubits. Here you and this here requires quantum Fourier transform, which is yet another circuit. This is QFT inverse, and here you have QFT again. So you get an impression what it means to implement this very fascinating, admittedly very fascinating algorithm if you really want to implement it on a quantum machine, right? You expand the depth significantly, and you also increase the width, the number of qubits that you do require in order to implement it. So implications are oracle expansion requires additional operations and additional qubits compared to the ideal algorithm that got described in a paper. Next thing now is connectivity. Connectivity means I must take a look at the at the chip, I must understand how the qubits of the chip are connected in order to be able to assess whether it can run on this chip. So we are really back to the 60s or 70s in the assembler time, where you must sometimes understand how the register is built. So we are now here taking again a look into the unitary transform proper. In order to understand what I'm going to discuss next is I remind what this controlled knot basically means. The controlled knot basically means I negate the state of this qubit y depending on the state of the qubit x. If the qubit x is in state 1, I negate y. If x is in qubit 0, I leave qubit y intact. So x is called the control qubit, y is called the target qubit. It's an if statement. If x is equals 1, negate y, otherwise go ahead, leave everything intact. And the set of 1 qubit operators and C0 is universal. So every quantum algorithm can be transformed into manipulations of individual qubits and applying a bunch of C0 gates. But there are hardware restrictions. Here's a very simple one of the first qubit chips, a 5-qubit chip that has this kind of connectivity. I mentioned in the introduction that the number of wires that you need in your chip in order to connect qubits introduces disturbances. That means each additional wire here introduces the reduction of the coherence time, introduces errors in the qubit. That means a chip producer wants to minimize the number of connections, but you cannot live without connections because you need physical connections between 2 qubits in order to run a C0, right? If you have 2 qubits, qubit 2 and qubit 4, and if you want to apply the if-then here, right, it must have a physical connection. So it cannot run a C0 between qubit 1 and qubit 3. So what do? Connectivity of a qubit is important. Ideally, you want to have an everything is connected with everything chip, but this introduces significant noise in the chip. You can't do that. Here you see sample connectivities. By the way, these graphs are called topology graphs, right? So here you see which qubits are connected with each qubit. And this is the chip, the Yorktown chip of IBM that I've shown before, and here's a chip of Rigetti, and it's a secret of a QPU vendor which topology graph they basically use, right? You see this graph is very different from this graph, and the QPU vendors, they basically understand the connectivity and the technology they use to build the qubits and the connections in order to manage the noise on the QPU. And I introduced already also as the swap operator in my last talk. A swap operator basically exchanges the state in X with the state in Y. This is in his so-called swap gate. It basically is this unitary map. 0, 0 goes to 0, 0, 0, 1 goes to 1, 0. So the first and the second qubit exchange their state, and the same is true. 1, 0 goes to 0, 1. And here 1, 1 is mapped to 1, 1. So the swap operator is vital. And the swap operator is neither implemented on a physical QPU, but you must emulate it by these 3 knots. So this circuit here, this C0, this C0, this C0, they implement the swap. In lectures, we typically prove it, right? That basically means the following. I have a very fancy algorithm, right? I invented this algorithm, and I now would like to show how this is transformed in order to be implemented on this machine. This is a theoretical 4-qubit QPU. And the assumption further is that each qubit in my algorithm is mapped to the qubit, so the physical qubit on my machine with the same index. So B1 is mapped to Q1, B2 is mapped to Q2, and so on. So what that basically means is, this is what I need to generate out of it. So because B1 and B2 is mapped to Q1, Q2, I can apply this C0 on these 2 physical qubits. That means this thing remains intact. Next, I want to apply a C0 between B3 and B4, but B3 and B4 got mapped to Q3 and Q4. They are not connected. So what I do is I swap Q2 and Q3. If I map Q2 and Q3, that basically after this swap, the formerly B3 contains now the information of B2, and the former B2 contains the information of B3. And now I can apply the qubit between B3, the C0 between B3 and B4, because this is now B3 and this still is B4, right? So this is the first rewrite. The next thing is that I would like to swap B2 and B3, but B2 and B3 have been exchanged. That means I need to reverse this C0 and implement this C0. The rotation operation remains the same, but here it is asked that I apply a C0 between B2 and B1. So what I do is I swap B1 and B3, because this B3 now is now in B1, and B1 is now here at this qubit, and here is B2 is in this, oh, sorry. So B2 is in this line, B1 now is in this line. That means this C0 is now this C0. And now I mentioned before that the swaps are not implemented natively in quantum on QPUs, but only C0s. That basically means this, each of the swaps got implemented by this series of C0s. And this then here is the final algorithm that resulted. So I invented an algorithm of depth 1, 2, 3, 4. And what I resulted in is an algorithm of depth 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? So very different. Right? So this is why I must understand the result of a transpiler to assess whether or not a certain circuit may run on a given machine. So, but this is even worse. Even worse means the following: the connections between the physical connections between the qubits have a different success rate, right? This is a success rate. These are, for example, in superconducting qubits, these are very often microwave connectors between the qubits, right? And their success rate varies over time. That means if you take a look at the topology graph, the topology graph will be annotated by numbers that say what is the current success rate. And let's assume that I would like to apply a 2-qubit operator to qubit 3 and qubit 1. Right? In order to do so, I must move Q3 to this position in order to apply it. But then I can, so if I swap basically Q2 and Q3 and then have a success rate, the success rate of moving Q3 to here is 0.3. And then the success rate of applying this operator omega on the now neighbored qubits is 0.5. That means the overall success rate of performing this operation omega is 0.1. But if I really take a look at the success rate, it turns out that swapping it multiple times, so Q3 to Q4, 5, and so on, up to Q8, gets a much higher success rate of 0.33. That means only a single swap, if you do it naively, using a single swap, has a lower success rate of using 5 swaps, and then followed by the 2-qubit operator that I want to apply. Right? So the success rate of qubit connections influences the number of the swaps performed as well as the error rate of the 2-qubit operations. And even worse, the success rates that are annotated on these connections change over time. That means this initial allocation of qubits in my program to physical qubits may vary over time. That basically means, here's an example. I have this program, I have this chip. So what the transpiler basically does is it considers the different success rates of the connections, and basically computes the success rate of the different assignments. I first assume that my qubits that I need in my program, Q0, Q1, Q2, are mapped to 1, 2, 3 here. The success rate will be 0.15. If I map it to 2, 3, 4, and so on. It builds this kind of a table, and then it determines the mapping with the highest success rate and assigns my 3 qubits to this physical qubits, and then does the execution. Here's a real example. This is a very simple circuit that I transpiled on IBM machine. And here IBM publishes the topology graphs in the color code. So IBM does not, this graph does not contain annotations on the edges, what the success rate is, but the color code basically indicates it. Although you can get the real numbers out of Excel spreadsheets. So you can basically use an API and then you get information out of the machine what the numbers of the success rates and decoherence times of the qubits are. So this is here the topology graph annotated with the success rate, and here you see the circuit that got transpiled, and here's the explanation, right? By the way, this U3 is the implementation of the Pauli X matrix, and here's a swap. Right, this 3 C0s is a swap operations, is a swap operation, and then you may reason why the transpiler transformed this thing here into this thing. So this qubit 1 got mapped to qubit 3. It has to do with the success rate of qubit 3 and the success rate of this connection. And so I'm not diving here into the details. All right, and even worse, this is, as I said before, time dependent. Because of time reasons, I did not add slides where I transpiled the very same circuit at very different times, because the quantum computer today must be recalibrated periodically in order to clean up the machine so that the decoherence time is high enough. So the machine is calibrated from time to time periodically, and then different transpiler result basically do result. So the implication of connectivity is, well, you need to inject additional swaps compared to the ideal algorithm. And the success rate of qubit connections influence the number of swaps that you basically need, as well as the error rate of the 2 qubit operations. And if you consider the success rate of qubit connections as well as error rates during qubit allocation, influences the reliability of the execution, as I've shown in one of the examples. Now, readout errors. So we now understand much better what it means to pump data out of the classical world into a quantum machine, perform the algorithms, and that I need to fiddle around a lot with the algorithm. So the ideal algorithm get significantly modified in order of depth and width, and even transpilation increases the depth. So the result appears as a quantum state in your quantum machine, and you need to get it out of a quantum machine. Reading something out of a quantum machine means you measure it in order to get a probability distribution, and then the probability distribution gives you an indication what the real result basically is. So what does measurement mean? So during measurement takes a long time, often significantly longer than decoherence time. That basically means while you measure a certain qubit, the qubit may relax, right, based on T1, T2 times, right? That basically means a qubit may flip from 1 to 0, and that means these readout errors correspond to disturbed probability distribution of the measured result. So the measured result is a probability distribution, but it is disturbed when compared with the undisturbed distribution, which is the real result. So what you can do is you can apply techniques from statistics that is often applied in particle physics, which is called an unfolding. An unfolding is a technique that reconstructs a true undisturbed distribution out of a measured disturbed distribution. There are several folding methods, and I only discuss the most simplest one. So let T be the true distribution and N be the measured distribution. Here we have this diagram. So the distribution is a distribution over certain values, Yeah, a quantum computer spits out a distribution on natural numbers. That means sequences of binary digits. The true distribution, how often this number occurred, is this white bar, and here the measured is the gray bar, right? This so T is a vector of natural numbers, M is a vector of natural numbers, and these vectors T and M are related by the so-called calibration matrix C. That means M is the vector of measured distributions of my result, T is the true thing, and C basically is the matrix that transforms M into T. Where this matrix C has the coefficients, well, the Cij is the probability that the measured result is J, but the true result should be I. And correcting readout errors means to determine this calibration matrix. How do we do that? Well, we do that based on these kind of circuits. So what I do is I take the ground state of my quantum computer and measure it immediately. Then I measure, so to speak, the true distribution of the measurement 0. Then I prepare my computer, my quantum computer, into the state 1, 0, 0, 0, and I measure it immediately. I prepare it in 0, 1, 0, 0, 0, measure it immediately, and so on. So what I do is application of each of the circuits Ci, and I basically is the vector that I prepare here, and I perform this state, this circuit m times, and if I measure j k times, then the coefficient of the matrix Cij is k divided by m, just like probability, right? Observed numbers divided by possible numbers. Here's an example. I prepare the vector 1, 0, 0, 0, and I immediately measured it on my quantum computer, and here's the distribution that I get out. And out of this measurement results, I can compute the column of my matrix, the first column, right? Because I measure 0, although the state that I prepared is the state 1, 0, 0, in 0.332%. This is this this is the distribution, 3.3%. This is this number here. I measured luckily 91% of the real result, 0.001, right? This is then the second column, and so on. So this is how I compute the individual columns of the calibration matrix. And that basically means in order to correct readout errors, I require additional operations, namely the calibration circuits, to determine the calibration matrix. But I don't need that for every execution of the ILD algorithms, because I only need to compute this calibration matrix if and only if my machine got recalibrated. Then I compute the calibration matrix again. And correcting readout errors itself requires classical post-processing, because then I need to apply the calibration matrix to the measured results. So what I need to do is periodically, not for every run of my quantum computer, for my quantum algorithm, I need the classical pre-processing. That means I prepare the column vectors that I want to measure. The column vectors, this is the column vector that I want to measure. This is the little circuit that I need to generate as a quantum assembler. I prepare then this state, execute this quantum circuit here, measure the result, which basically means I get the column of the calibration matrix, and then I store this calibration matrix. And then if I run my real algorithm, then I read out the result T, and then I get the measured distribution M, and then I need to unfold it by applying the calibration matrix, and then this is the result. This is corrected. This sounds to be a lot. And of course, being a computer scientist, we want to help our users, and we one of the work that we are doing is we build a Nisk Analyzer. While analysis is a bit we do a bit more. So first of all, we are assessing whether a certain circuit may run on a given machine. So first of all, we have a machine with an error-bound epsilon. So what we do is we analyze the circuit and say, can it be executed based on the depth and width that the algorithm has? And applying this thing here, the user can pass to us a bunch of machines, and then we basically say, okay, here's the circuit, please run it on this machine. The highest success rate will be on this machine. In order to do so, we need information about the different quantum computers we have access to. That means we need provenance information. So provenance, if you know as a computer scientist, is information that describes processes, computations, or data. And the goal is to ensure reproducibility, understandability, or quality of the processes, computations, data. And why is it important for quantum computing? It's important because our machines are all noisy, decoherence time, gate infidelity, and that like connectivity. And there are many different hardware implementations, superconducting machines we have access to, trapped ion machines. We don't have access to optical, but we will have access to cold atom machines very soon. So this is provenance information that we need. And the information that we get out of these machines, and luckily the machines have APIs that you can use to retrieve this kind of information that we need. For example, the gates that are available on this machine, the topology graphs that the machines do implement, they document spam errors. Spam means state preparation and measurement errors, right? How many errors occurred during measurement of a single qubit. This is information that we basically get out of the machines. And then we collect this information on the right side and store it into a provenance database. We store other information into the provenance database, for example, the calibration matrices that we have of these machines, because we need these calibration matrices are important provenance information. I need them in order to correct measurement results. Then we analyze different algorithms and store the results like the depth and the gates to be performed also in the provenance database. And I can skip over it. And then I can basically use the information. Here comes a circuit, right? Then we have a translator, and this translator basically has plugins in order to translate a certain circuit into representations that different environments need. So there's a Qiskit plugin that basically translates the circuit into a format that IBM can understand, or we use a Forest plugin in order to generate a format that Rigetti machines can understand, and that like. And the rewriting stages mean here comes the algorithm. We inject data preparation. We prepend data generation, data state preparation circuit, sorry, that we generate as I've shown before and prepend it to the circuit proper. Then we find out that there are oracles, and we substitute the oracles by oracle logic that we store in certain libraries in order to expand then the oracles. Then we substitute the gates. So this ideal algorithm uses some gates that the real machines, the QPUs that are listed on the left, do not support. That means we need to rewrite the gates of the ideal algorithm into the gates of the real machines. Then we need to have the other provenance information. What is the quality topology information about the machines and so on. And then we have the rewritten circuit, and then we assess the execution readiness. Can the rewritten circuit be executed on one of the machine? And here in this sample, we show, okay, QPU1 and QPU3 may successfully execute the machine. And then once the user decides which machine to use, we generate a code that does the error mitigate, the readout error mitigation, right? No, first of all, we prepare the calibration matrices, and then we basically generate the code for the mitigation itself. And then there's a NISQ recommender. We make it much more convenient. This is what we discussed before. So the user comes with a circuit. The circuit is then translated according to certain environments where the circuit may be executed. Then it is transpiled, and we have a plugin-based concept. We can use different transpilers that are available in order to transpile the circuit. The transpiled circuit are then evaluated based on the provenance information, right, on which machine may the circuit be executed. Then the user may define its preferences in terms of, do I value cost of the execution higher than speed of the execution, and so on. There are some methods that we can that we allowed to subscribe. Then based on these methods, we spit out ranked results of the transpiled circuit, and then the user may basically say, okay, please execute it now here on IBM-Q, on Rigetti and IMQ, and so on. Then the measured results comes out, and after some while, the user may basically say, okay, here's the measurement results, please adjust the weights again, and then the ranked list will become a different one. So this ends the talk with a summary. The summary is the current machines are the NISQ machines, noisy intermediate scale quantum machine, and these machines are determined by decoherence, by gate infidelity, readout errors, the physical implementation of the chips, the connectivity. You need to have data preparation and other problems. Measurement is another problem that I mentioned. But all these problems can be addressed, but require additional gates and qubits. This is also what I tried to highlight. And that basically means you need much more resources, much more qubits, much more lengthy algorithms than may be available. And I briefly sketched a component that we call the Nisk Analyzer, but there's also a rewriter and recommender. This is a tool that helps to determine which QPU is the best to solve a problem based on a given algorithm under given constraints like cost and precision. And on Friday, we will also present another component called QANA, which is a tool that allows you to prepare different implementations of algorithms classically and quantum with different hyperparameters in order to compare the results, to get a feeling, to make an assessment when it does make sense to use a quantum machine or not. So this ends the talk, and I stop sharing and take a look at the questions. Where's my...
Also, Frank, many thanks. Yeah, it was really, as always, brilliant and a lot of information, very dense. There are a couple of questions, but beforehand, I got also some in the private chat some remarks. Would it be possible to share your slides?
Absolutely, sure.
Okay.
Yes.
So the best thing is that you mail them to me, and we. Is it possible that we make them available on the website?
Absolutely.
Okay.
And so the slides basically cover a paper that Johanna and I have written. I can share the paper as well.
Thank you. So the people are now online, and there are really quite a few. I'm really very happy about that. Have heard your answer also, and the others will see it. There is a very good question from, I guess, from a computer scientist, where he or she asks, what is the role of computer scientists in doing the work without having a math and physics degree like you have?
So let me start with the first comment. I always use that in nearly every talk. So I work together with quantum physicists that work on quantum computing. Mm-hmm. And when I bumped into one of a very, very famous person, this is why I don't mention his name here. So I asked, dear Mr. Physicist, you build quantum algorithms. How do you test them? He said, well, test? Why should I test them? I said, because you can introduce errors. And he said, and he meant it serious, I'm a physicist, I don't make errors. So this basically makes it clear that you need it. But now a much more serious answer. The much more serious answer is that quantum algorithms are always hybrid. That means a quantum computer is a specialized processor. It's specialized in performing particular tasks extremely well, often exponentially faster, exponentially more precise, accurate than the classical thing. But what you need is, now I come back, you mentioned that I worked on workflow, what you need is, so to speak, in real world application, A lot of stuff happens before you dive into a quantum computer, and a lot of stuff happens after the quantum computer. And having said that, you will immediately see is that we as computer scientists need to solve an integration problem. We need to find out what are the problems that we need to solve. How do I break it down into pieces, divide and conquer, and then find out which part is suitable for a quantum computer, while the vast rest, the majority of the problems is classical computing. So, right, so this is absolutely serious, and this is what we begin to I get nervous, right? Because the question is absolutely fantastic, right? So we need classical computing, classical computer scientists, because quantum computing is only a tiny part, a key part in solving a particular problem, but the rest is computer science.
Okay. So I also have a look at the chat, but I would also have a question. You know, there are these quantum programming languages coming out.
Yeah.
Now, how does this align with also your presentation, in the sense of, does the existing quantum programming language already take some work from, you know, doing all this adaptation, or nevertheless would this has to be done also using a quantum programming language?
So first of all, there is the very basic language, the quantum assembler, and this OpenQASM 3.0 that I mentioned a couple of times becomes an industry standard. The industry is sitting together, they build a consortium to do it. But each and every vendor builds a collection of library. Most often they use Python in order to solve these problems, but they solve only problems that are very narrow to a particular algorithm. For example, if you take a look at Qiskit or Penny Lane, right? They implement Shor algorithm, and then they implement a little bit of pumping data into their implementation of the Shor algorithm. But what you do is, and now I'm now speaking with a couple of years of experience in real applications. What the people want to do is they want to have a circuit, what real companies want to have a circuit, and they want to run it on Penny Lane and IBM and Rigetti and fiddle around with it. And in some problems, you need a D-Wave computer in the first step, and then an IBM computer on INQ in another step. So you need to build a workflow. Let me abstract it into integration solution, because what we also did is we fiddled around with low code. Low code is something very famous, very modern. We worked together with a company called WSO2. They have a low code tool, and we enabled their low code tool also to interact with quantum computers. So you have a real workflow, and if you rely on a single environment of a company, you are bound to it. You need to rewrite it any time. So what we are doing, we computer scientists, what we are going to do is very valuable, because it guarantees portability across different environments. Right? This is what people really want to do. Companies that we work with, they have access to different machines, and they always want to use the different machines, and they don't want to rely on Qiskit only and Penny Lane and so on.
So now there are quite a few questions. I just read the last one. How fundamentally different are the topologies of the quantum chips and computers in your experience? How many of them are there?
Every chip has a different topology, Sharon.
Oh,
okay. So very different. And they change from generation to generation. So IBM is built now a new chip as a completely different topology. And many computers are available for free online. And if you transpile the same circuit to the different GPUs of IBM, they result in very different transpilation results. But it's very different. Another question is, what do you think of the future of Quawa? Right, so Quawa means it's a variational quantum algorithm. Variational means, as I said before, each and every quantum algorithm, even the Shor algorithm, the very famous Shor algorithm, is hybrid. It does a little bit quantum, and then you do much in a classical computer, like this continuous fraction analysis. So, and as I said before, quantum algorithms should have a small depth. That means only very few layers may be executed on a quantum computer. And the trick is to break a lengthy algorithm into parts. to run only the first few steps, measure, run the next steps, and so on. And if you, and special kind of problems do that, they prepare circuits with parameters. Then you run a circuit with the parameters, for example, the angles in which you rotate on a Bloch sphere. Then you measure it compared with a loss function, the Ziel function. You run optimization problems with a loss function. You optimize the parameters on the classical machine, change the parameters, go again into a circuit, then you do it in a circuit until your circuit has been trained, so to speak, until you get your results. So this is what people do today, variational quantum algorithms. And they will stay not forever, but I give you an indicator. What IBM has done recently is this language, OpenQASM 3.0, is a language that allows you to write classical code and quantum code in the same language. And they do that because you analyze the code. Out of the classical code, they really generate classical code, in fact, function as a service, and then the quantum circuit remains. And they run it in their new runtime iteratively in order to make this variational algorithms very, very fast. This is an indicator that this company believes that this kind of variational circuits will remain there forever. Even further, they envision multiple runtimes. So the prototype we built with them is based on workflows for long-running applications, because we already have applications in chemistry and also in machine learning where the application runs for minutes, for hours. I have a customer that runs it for days. This requires a workflow technology. That means interruptible computing. If error occurs, you don't want to restart again. This is another runtime they envision based on the prototype we did with them. Yet another runtime is a runtime that combines HPC and quantum, because there's something very fascinating that is called warm starting. Warm starting means the following. If you have NP-hard problems, many of them can be solved approximately, but many of these approximation algorithms are proven to have a boundary around a fixed boundary, a hard boundary around the optimal result. For example, Leymann-Williamson, it's a very famous algorithm for max cut. You can prove that you can only approximate the real solution up to 87%. But then a couple of years ago, during a Dutch school seminar, a team has proven that if you have an algorithm that uses entanglement, this is what I'm going to discuss in 2 weeks, that uses entanglement, you can break the boundary. You can do a pre-computation on a classical algorithm to get close to the boundary, and then you have the pre-computed solution. You warm start your quantum computer with the pre-computed solution to jump into jump across the wall into the boundary. This is then and what people think is you use a high-performance computer, an HPC, to pre-compute something and then go into a quantum computer and even get a more accurate solution and so on. And these kind of runtimes, there are multiple of these runtimes. This is another research item we computer scientists may work on. What are proper runtimes? If you lean back, that basically means how do we do requirements analysis? How do we break down problems into bundles of problems that can be executed in this kind of runtimes? A lot of new and fascinating computer science problems are coming up. So this was triggered by Quava.
No, but what about the Nisk Analyzer tool? Is it available for usage?
It's on GitHub. Yes, it's on GitHub. It's in beta, so we still know what to do, but anybody can download it and play around with it.
There's this, what will quantum computing be able to do in 10 years?
Bomb us back to Stone Age, which is my famous, because we will be able to break encryption in the next few years. So what I'm absolutely fascinated and shocked about is how fast the quantum computers do improve. So my old friends from IBM, they tell me we do this in 1 year. They are always underestimating. So when I ask people, when do we will have 50 qubits 2 years ago, they say in 5 years. But 1 year later, they had a 50 qubit computer. And then I asked them, when will we have a 100 qubit computer? They say mid of the decade. They just have the computer online for selective customer, 127 qubits now. They will have about 400 qubits end of next year, 1,000 qubits in 2023. And they envisioned 1 million qubits by the end of this decade. Years ago, I asked Jay Gambetta, who is the lead technician, the IBM fellow behind quantum computing. He told in a public talk, I invited him, when will you really have this 1 million qubits? And he said, very likely. And then I said, a couple of months ago, I invited him again. I asked him the same question, and I asked the question, how many logical qubits will this be? I told you before that there's a factor of 1 to 1,000 to build out a physical qubit, a logical qubit. And he shocked me. He basically said, I think we have technology experimentally built where each physical qubit will be a logical qubit. If this is true, we will have 1 million logical qubits within a decade, and then we can crack each and every key. That means no online banking, no online shopping, nothing. All documents that companies store today that are encrypted and must stay encrypted for a long time for audit purposes can be cracked. So companies should start now to think about a strategy, how to encrypt data, how to protect data. So they already have a problem now, right? They have a problem now because they must think about how do I protect this data in future once these quantum computers are available and powerful enough.
Okay.
So
a lot of things for computer scientists to do. There's another question about
if you have post-quantum computing. Yeah. This is a related question. PQC. Yeah. PQC means, well, if I have RSA today, can we use different security technologies? Yes, and the person who asked the question knows post-quantum security. We are investigating, that means NISQ is investigating algorithms that are quantum safe today, and that can't be cracked with today's classical algorithms. That means we are basically betting, we are identifying algorithms that are hard to crack classically and quantum, but there is no guarantee. You cannot prove that they can't be cracked. This is why agile cryptography is so important. That means people are currently thinking about how do I build a security infrastructure that exchanges the encryption, decryption algorithms periodically or randomly, right? And if one algorithm is cracked, we immediately pull the plug and use other algorithms. This is a new agile security infrastructure that people build. What is the architecture for it? How can we build that into our system, right? And another thing is how do we exchange keys? So symmetric keys can't be cracked. You can prove that there are bulletproof quantum algorithms of exchanging symmetric keys, but then we need a completely new infrastructure because it is based on entanglement. We need light fibers, we need laser lines between all our locations. A lot of stuff needs to be done in order to protect us here.
There's the last question. There was a question about if you know anything about this IBM Eagle quantum computer.
This is the new 127 qubit computer that is available since a couple of days for selective customer, and from January on for many more people. Yes, and this is it has a higher decoherence time. It has 99.9 2-qubit fidelity, and it is extremely fast. IBM introduced, and others already start with it. They introduced now a measurement of the speed of a quantum computer called CLOPS, German, but strange, circuit level operations per second, like flops, right? And they basically shown a diagram a couple of days ago that they are on an exponential path to increase this CLOPS number.
Mm-hmm. Well, so before we continue for hours, I guess I want again to thank you. I'm really looking forward when you come to Vienna, hopefully in springtime.
I hope so, yes.
But before, kind of as advertisement, the next talk will be coming Friday on the 26th of November at 2 p.m. Also everything online. And,
but in German, Gerti, in German, because the slides are all in German.
Genau, da kann ich jetzt auf Deutsch, weil der wird auf Deutsch sein. Genauso dann der übernächste Vortrag am 10. Dezember um 14 Uhr. Der ist noch nicht online. Wir wollten heute abwarten und gehen dann damit online. Diese beiden kommenden Vorträge sind auf Deutsch, werden aufgezeichnet und stehen dann auch zur Verfügung.
Ja.
Genau. Frank, once again, thank you very much. And I'm looking forward to all the next presentations.
Will do. Have a good time.
Thank you to the audience.
Bye. Bye.